Thank you very much for tuning in to my virtual webinar about composite ab initio methods. Not every day I get a chance to talk to leading physical chemists, so I would like to start with a very relevant topic, the Journal of Chemical Physics Letters. The journal was established over 50 years ago, and the scope of the journal covers all aspects of physical chemistry. So, for example, developments in theoretical and computational chemistry, new experimental methods, nanostructures and nanomaterials, energy conversion and storage, biomolecular systems, polymers, and gas phase chemistry. The editors of the journal are David Clary from the University of Oxford. David has been one of the leading editors of the journal for over 20 years now. We also have Benjamin Dietzek from the University of Jena in Germany and Kelly Han from the Dalian Institute of Chemical Physics in China. I joined the editorial team recently, and I'm very happy to be on board. In this context, I should also mention Michio Okamura, who has been an editor for many years and has recently retired. Over the years, ChemPhysLet has published many papers in the development of theoretical and computational methods, and I would just like to mention some of these papers here. I will also talk about some of these papers in quite some length today. The paper that developed the so-called CCSD parenthesis T method was published just over 30 years ago by Krishna Ragavachari, Martin Head Gordon, John Popel, and others. This method is known as the gold standard of computational chemistry and is of key importance in composite ab initio methods. One of the papers that developed the polarizable continuum solvation model was also published in ChemPhysLet in 1996. A key paper that developed basis set extrapolations, which are also of key importance in composite ab initio methods, was published in 1998. The paper that developed the CAM-B3-LIP method was published in 2004. In the same year, a number of papers that describe explicit correlation methods were published in ChemPhysLet. In 2011, Don Truller published an important paper describing the Minnesota functionals. And if I can get away with mentioning one of my own papers that was also published in 2011 and develops a thermochemical database of total atomization energies. ChemPhysLet has a very high visibility around the world, and this is particularly true for countries like the United States, China, and Germany. And I would like to show you some of recent papers that are fairly highly cited. I will flick through these papers fairly quickly, but this is just to show that papers published in ChemPhysLet can be highly cited, and submissions from Australia and New Zealand are very welcome. So let's move on to an introduction to composite ab initio methods. In this short presentation, I won't be able to go into too much detail. I will only be able to give you a taste of the topic. So I'm listing here a number of excellent reviews that cover composite ab initio methods, and you are very welcome to check them out. Composite ab initio methods are used for obtaining highly accurate thermochemical and kinetic properties. So, for example, things like reaction energies, enthalpies of formation, reaction barrier heights. They can also be used for calculating highly accurate molecular structures and spectroscopic and electrical properties. So there's a very clear chemical motivation for using composite ab initio methods when we want to calculate these chemical properties with high levels of accuracy. A theoretical motivation for using composite ab initio methods is for calculating highly accurate chemical properties for the parameterization of more approximate theoretical procedures, most notably for the development of better and more accurate density functional methods. It's always good to have a slide with a Feynman quote in any scientific presentation, so here's mine. It doesn't matter how beautiful your theory is, if it doesn't agree with experiment, it's wrong. And I imagine that Feynman was implying the word reliable here as well. So in this presentation, we will see how we can benchmark the most accurate quantum chemical methods against very, very accurate experimental data. But in contrast to, say, 30 years ago, when supercomputers were not as strong and our theoretical methods were not as refined as they are today, we would normally see this interaction between theory and experiment. So the experimentalist would go to the theoretician and say, your calculations disagree with our experimental results, therefore your theories are wrong. Today we have a more balanced relationship between theory and experiment, and often it can go the other way. So the theoretician would go to the experimentalist and say, your results disagree with our very accurate calculations, so go and check your experimental results again. But it is important to mention that even though we have a more balanced relationship these days between theory and experiment, this does not mean that every result that we obtain with density functional theory, or even with a composite ab initio method, is necessarily correct. And we always have to make sure that we are obtaining the right answer for the right reason. So how can we compare between theory and experiment? In order to visualize this, we can imagine a three-dimensional cube. Here we have our wave function axis. So we start from the Hartree-Fock wave function, and we include more and more electronic excitations in the wave function. Here we have our basis set axis, and we can start from a minimal basis set and expand the wave function using larger and larger basis sets. If we use an infinitely large basis set, and we include all possible electronic excitations in the wave function, then by definition, we calculate the exact non-relativistic electronic energy. Now, in order to compare this energy with experiment, we have to consider secondary energetic contributions, so things like the zero-point vibrational energy, relativistic corrections, and deviations from the Born-Oppenheimer approximation. If we calculate all secondary corrections with a high degree of accuracy, then we obtain a highly accurate theoretical energy that we can directly compare with experiment. Now, the point of this slide is that composite ab initio methods can do all of this. So they are methods that were specifically designed to calculate all of these steps with a high level of accuracy and to obtain accurate energies that we can directly compare with experiment. Well, now I got myself into trouble because the computational chemists in the audience will say the only systems for which you can include all possible electronic excitations in the wave function and run these calculations with a very large basis set are very small molecules like diatomic and triatomics. So for larger systems like benzene, naphthalene, or even larger, how can we obtain highly accurate energies that are close to the exact solution? Well, this is where basis set extrapolations and other basis set acceleration techniques come into play. So let's look at what is computationally feasible for a fairly small molecule, propane, with 20 valence electrons. So here we see the Pople diagram with the wave function axis here and the basis set axis here. And the key point to note in this Pople diagram is that as we include more and more electronic excitations in the wave function, the computational cost increases in an exponential manner, and we can run these calculations only using smaller and smaller basis sets. So by the time we include all possible excitations in the wave function, we can afford these calculations with a very, very small basis set, which for propane would be smaller than a double zeta basis set. So if this is the computational space available to us, how can we obtain energies that are close to the exact solution? So this is where basis set extrapolations come into play. And in the composite methods that I'm going to introduce today, we use two-point basis set extrapolations. And that means that for each of the energetic components, we will run an additional calculation using a slightly smaller basis set. So we run all of these additional calculations that have a lower computational cost than the calculations that we already ran with the larger basis sets. Now, because of the systematic behavior of these basis sets, in these cases, the correlation consistent basis sets, we can take these two energies and extrapolate them to the complete basis set limit or the infinite basis set limit. So we can do this for all of the energetic components, and a key feature that the composite methods rely on is that as we go to higher and higher excitations, the basis set convergence is accelerated, and we need smaller and smaller basis sets in order to approximate the infinite basis set limit. So now we are going to take all of these energy components and we can sum them up and obtain an estimate to the exact non-relativistic electronic energy. So generally speaking, composite ab initio methods could be divided into two categories: the more rigorous non-empirical methods. These methods involve calculations of at least the CCSD parenthesis T level, but often they include contributions beyond that. These energies are extrapolated to the infinite basis set limit using very large Gaussian basis sets, and secondary energetic contributions like relativistic effects and deviations from the Bohr-Oppenheimer approximation are taken into account explicitly. Methods of this type include the Weizmann-N methods of Jan Martin from the Weizmann Institute, the heat protocols of Gauss and Stanton, the Feller-Peterson-Dixon methods, and the CCCA methods of Angela Wilson. Now, these composite methods are very rigorous, they are very accurate, but they are also applicable to fairly small molecules, and I will talk about this in one of the next slides. Empirically corrected composite ab initio methods involve lower-level CCSD parenthesis T calculations. These energies are not extrapolated to the infinite basis set limit, but rather they use basis set correction terms obtained from Moeller-Plesset perturbation theory. Secondary energetic effects are not always taken into account explicitly, and this means that in order to obtain high accuracy, these methods need to include empirical terms that are parameterized against accurate experimental data. Because these methods are computationally much more economical, they are applicable to much larger systems than the non-empirical methods and are therefore very, very useful. Methods of this type include the Gaussian N methods of Krishnan Raghavachari and co-workers. In this context, I should also mention the G4MP26X method of Boon Chan and Leo Radem, and also the CBS methods of Peterson and co-workers. Here I will mainly talk about the non-empirical methods. These methods can again be divided into two basic categories: what we call post-CCSD parenthesis T methods that try to approximate the exact energy, and CCSD parenthesis T methods that try to approximate the CCSD parenthesis T energy close to the complete basis set limit. The accuracy of the post-CCSD parenthesis T methods is normally within plus or minus 1 kilojoules per mole, and the target accuracy of the CCSD parenthesis T methods is normally within plus or minus 1 kcal per mole. So let's ask the following question: how well do post-CCSD parenthesis T composite ab initio methods perform relative to very accurate experimental data? And when we are benchmarking these very accurate theoretical procedures, we are going to do it for total atomization energies. The reason for that is that total atomization energies are one of the most challenging chemical properties for electronic structure methods. A total atomization energy is the energy required to break all of the bonds in a molecule and to separate it into the free atoms. So in a molecule like phenol, for example, we have 6 aromatic CC bonds, 5 CH bonds, 1 CO bond, and 1 OH bond. And if you sum these bond energies up, you will quickly reach energies exceeding 5,000 kilojoules per mole. And the target accuracy of post-CCSD parenthesis T composite methods is plus or minus 1 kilojoule per mole. So this is quite remarkable. We would like to calculate an energy that can exceed 5,000 kilojoules per mole with a target accuracy of only 1 kilojoule per mole. Okay, so let's see how we go. Now, when we benchmark these highly accurate theoretical procedures, we have to use highly accurate experimental data. Here we would like you to use experimental total atomization energies with error bars that are equal or smaller to 0.2 kilojoules per mole. Now, such highly accurate experimental data is only available for a fairly small number of systems. Here we have gathered a set of 35 experimental total atomization energies with error bars that are equal or smaller to 0.2 kilojoules per mole. And when we benchmark one of our post-CCSD parenthesis T composite methods, one of the WN methods, in this case we're benchmarking the W4 method, we get a root mean square deviation of 0.36 kilojoules per mole, which implies a 95% confidence interval of 0.7 kilojoules per mole. This means that any total atomization energy that is calculated with the W4 composite ab initio methods will have an error bar of plus or minus 0.7 kilojoules per mole, just below the 1 kilojoule per mole mark. So this is really great, but the downside is that these methods are computationally so expensive they are only applicable to fairly small molecules. So molecules like acetic acid, glyoxal, CF4, and so on. So these methods are indeed highly accurate, but they have limited applicability. So let's move on to methods that are still post-CCSD parenthesis T methods, but are computationally less expensive. These methods are called CCSDT parenthesis Q composite ab initio methods, and in these methods we neglect all of the terms above the quadruple excitations, and the connected quadruple excitations are treated in a quasi-perturbative manner. These approximations will result in a significant reduction in the computational cost, but it has to come with a warning. So here we see the errors that will result from neglecting these high-level terms for a number of highly multi-reference systems. So for example, for ozone, a very famous multi-reference molecule, neglecting these high-level terms will result in an error of about 2 kilojoules per mole, and for C2, it will result in an error of about 3 kilojoules per mole. So the CCSDT parenthesis Q composite ab initio methods can no longer achieve accuracy within 1 kilojoule per mole for total atomization energies of highly multi-reference systems. Here we see a number of composite ab initio methods from the Weizmann N family that belong to this category. So we have methods like W4 light and W3. Here we see the root mean square deviations that we obtain against highly accurate experimental total atomization energies and the associated 95% confidence interval. So while we can no longer achieve 95% confidence intervals that are smaller than 1 kilojoule per mole, we still obtain very respectable error bars with the CCSDT parenthesis Q composite ab initio methods. Here we see the applicability of CCSDT parenthesis Q composite ab initio methods. So we can see that they're applicable to much larger systems like benzene, the phenyl radical, pyridine, and even C2Cl6 and the SF6 anion. Nevertheless, most chemists would still say that we can't do a lot of chemistry with these systems. So let's move on to composite ab initio methods that are computationally more economical and are applicable to even larger systems. So let's move on to the CCSD parenthesis T composite ab initio methods. These methods are much more popular and are applicable to much larger systems than the post-CCSD parenthesis T methods that we talked about so far. Here we see the computational scaling of the post-CCSD parenthesis T terms. We can see that they scale to the power of 3, 4, and 5 with the number of electrons in the system, and to the power of 5, 6, and 7 with the number of basis functions in the system. In contrast, the CCSD parenthesis T method scales to the power of 2 and 3 with the number of electrons, and to the power of 4 with the number of basis functions that we are using. So the CCSD parenthesis T method is applicable to much larger systems, but we will see that this reduction in computational cost comes with some sacrifice in the accuracy and the applicability of these methods, especially to multi-reference systems. One of the reasons why the CCSD parenthesis T method works so well at a modest computational cost is because the systematic error cancellation between the neglect of the higher order triple excitations and excitations beyond that. This error compensation works remarkably well for systems that are dominated by a single reference configuration, and for those systems, this approximation would normally result in errors that are up to 1 kcal per mole from the full CI CBS limit. However, for multi-reference systems, we have to be very careful when we apply the CCSD parenthesis T method or any composite ab initio method that is based on the CCSD parenthesis T method and does not go beyond that. So here, for example, we see errors for highly multi-reference systems that result from the neglect of terms beyond CCSD parenthesis T. So we can see that these errors can reach up to 20 kilojoules per mole for highly multi-reference systems. So for example, for ozone, which is a highly multi-reference system, the neglect of post-CCSD parenthesis T terms will result in an error of about 12 kilojoules per mole. This is an unacceptably large error for a composite ab initio method. And for large carbon clusters, we will get errors that are even larger than that. So it would be very useful if we could assess the degree of multi-reference character of a system before we apply a CCSD parenthesis T based composite ab initio method to it. Such a diagnostic exists. It's called the percentage TAE parenthesis T diagnostic. I don't have time to explain how this diagnostic works, but it is described in these references here. So now that we know not to apply CCSD parenthesis T based composite ab initio methods to multi-reference systems, let's look at the applicability of these methods. So for example, the Weizmann-1 composite method is applicable to systems with up to about 20 carbon atoms. So we were able to apply it to dodecahedrine, coraniolene, and sumanine. And we were able to apply the lower cost G4MP2 composite ab initio method to systems as large as C60. We were also able to apply the W1 method to DNA bases like adenine and guanine, and to amino acids like arginine, histidine, and phenylalanine. So let's look at the performance of composite CCSD parenthesis T methods. And here we will examine the performance of W1 theory. We benchmark the performance of this method against a diverse database of 183 total atomization energies, all obtained at the full CI-CBS level of theory. Now, these 183 total atomization energies were obtained for systems that we deem not multi-reference, according to the percentage TAE parenthesis T diagnostic. Now for this database, W1 theory attains a root mean square deviation of 3 kilojoules per mole, which implies a 95% confidence interval of about 5 kilojoules per mole. This means that the error bar that we can attach to any total atomization energy that we calculate with W1 theory is plus or minus 5 kilojoules per mole. On my last slide, I would like to show you an example of where W1 theory played a key role in a critical evaluation of experimental data. So here we see the experimental heats of formation of benzene, naphthalene, and anthracene. We can see that they sit on a straight line, and they are all associated with fairly small error bars of below 3 kilojoules per mole. Now, this is a homologous series, and we can pass a straight line through these points to get an estimation of the heats of formation of tetrazene. And if we do that, we get an estimated heat of formation for tetrazene of about 300 kilojoules per mole. Now, the problem is that the experimental heat of formation for tetrazene is over 40 kilojoules per mole above this estimated value. And to make things worse, the error bar associated with this measurement cannot possibly account for this very large difference. So in a case like this, it's very useful to be able to apply a composite ab initio method to calculate these heats of formation. And we did that with W1 theory. And for benzene, naphthalene, and anthracene, we get a fairly good agreement between theory and experiment. And for tetrazene, our theoretical value is much closer to the estimated value from the homologous series. So these calculations suggest that the error bar associated with this measurement is much larger than what we see here. Okay, so I see that I'm running out of time, so I would like to very quickly wrap up and thank the Raki Physical Chemistry Division and especially Laura McCamish and Taki for organizing this webinar series. I would like to thank the Australian Research Council for a future fellowship and our national supercomputer facilities. Above all, I would like to thank you for tuning in to this webinar, which should be available online afterwards. Thank you.